In this example, we're going to work start to finish with a differential equation that is first order, and it has two equations, two unknowns. The challenge is those two unknowns have derivatives involved as well. And what we are specifically going to do is go through the process that leads to x1 equals some function of time and x2 equals some function of time. What's the predicted value for x1 and x2 given the rules defined by these differential equations? Our first step is going to be to write this out in matrix form. We're going to take a time derivative of x1 and x2. Here we don't need new variables because we've got a first order system already. In earlier examples we had second order equations and we had to convert them, but these are already first order. So how can we actually create those? Well, we just take a look at our right hand side and rewrite it with the unknowns as a column vector here. So we see x1, x2, x1, x2. The difference is on the left hand side we're taking the derivative of those two functions. On the right hand side there are no derivatives, so we can simply write the coefficients down. There's 3x1s and there's negative 4x2s, there's 4x1s and negative 7x2s, and if you do the multiplication you'll get exactly this differential equation system again. Here it's just written out in matrix form. So no calculations, just separating the coefficients and the variables. That's all that happens in this transformation step here. When working with the matrix and vector form of our differential equation, it helps to have some rules for how we can construct our solution at the end of the day. When we talk about x1, x2 as a vector, what do we put on this right hand side? Well, we rely on some theory here, and it's actually quite general theory. Our matrix A is a bunch of constants, but it's possible that it could be a functions of time in there. And what we could have is a system as complicated as this. X prime plus ax, this is what we have here, but it's also possible to have another function outside of that contributing to the whole differential equation. So again, very general. And what we're told is that there's going to be a unique solution for a set of initial conditions. Fair enough. I think you'll find this part down here a little more familiar though. If all that other stuff is said again, and we look at the very specific case without the f of t, so again, this is what we have, then the solution we get is going to be some linear combination of, well, how many functions do we have? We have n functions of n linearly independent solutions. So we are going to build solutions, and we are going to then multiply them by C1 through Cn. In our case, here with a 2 element, we'll have a C1 and a C2, and then we're done. But we're going to have a linear combination of solutions, and that will make our general solution. So we've seen the kinds of solutions we will be looking for. We won't build them yet. We're going to do baby steps along the way, and first just talk about verifying solutions to get familiar with the kind of notation and structure we're talking about, especially because we have now these vectors and matrices involved. Here is exactly that scenario where we have the derivative of some unknown. Here's our scenario again where we have the derivative of an unknown function, some matrix times the vector of unknown functions again. What we'd like to do is show that there are solutions to this and that we can demonstrate those solutions in the same way we did it before, and we will verify in the same way we did before. We'll figure out the differential equation here, and what we're going to do is plug in our solution into the left hand side of the differential equation and see what we get. Then we'll plug into the right hand side, see what we get, and if they're the same, then by what we mean by an equation, we have a solution that satisfies the equation. The left hand side is nice and simple. So in some ways, this verification is a lot more straightforward than it was with higher orders. Now the verification step here in some ways is easier than it used to be. The left-hand side is just the first derivative of our x1 here. We said this is our x1, so we take the derivative, and it'll be element by element of e to the 2t. And that will be a collection of 2, 2, and 2 e to the 2t. And if you want, you could write this out as 2 e to the 2t times the vector 1, 1, 1. Sometimes it'll be helpful to write it this way, other times it's tidier, I think, to write it that way. Just know that both are perfectly equivalent because we can multiply this in and we would get that vector there. Looking at the right-hand side, we have our matrix 0, 1, 1, 1, 0, 1, 1, 1, 0, and times x of t, which we just said was e to the 2t, e to the 2t, and e to the 2t. So we're plugging this solution into here, then taking the derivative. We're also plugging it into here on the right-hand side. And if we do our matrix multiplication, we're going to end up with, on the first row, we're going to have e to the 2t plus e to the 2t. On the second row, we'll have e to the 2t plus 0 plus e to the 2t. I think you can see where this is going. And then we'll have e to the 2t plus e to the 2t plus 0. So I'll have 2 e to the 2t's. And just saying that out loud made it real. We'll have 2 e to the 2t's times 1, 1, and 1. And these are equal. And so we get a check mark.